Okay, example 9. Thank you. We'll start. By now you know. Can I have attention, please? Example 9. We're left with 3 more examples. I say keep the ball, right? Just keep the ball. All this recorded, eh? Oh. Okay. Where was I? Oh. I asked a question to the other lecture room the other day on Tuesday, and I keep repeating the same thing. Anyway, I kept repeating and asked them, am I very lost? Then they said, yes. So I decided not to say so much today. Or let's move a bit faster. Because actually, you are well equipped with the principles to solve all the problems. But I'm just going to expose all of us to some, what I call non-standard problems. That means not a standard one where you just find p-value, compare against level of significance, and conclude. You have enough of that. Okay? Okay? Okay. First such example is example 9, where you want to test whether now a lot of unknowns. You look carefully. We have K. We have sigma. We have N. In this case, then we cannot use EC to find p-value. In fact, it didn't even ask for p-value. Alright? So let us see how we do this. My advice is this, as I told my tutorial classes. You see standard problem, you see non-standard problem, do the same thing, follow the 6 steps. Okay, so state the hypothesis, state the null hypothesis. This is step 2, the step 1 is the definition, but nothing to define because nothing basically. They already define mu for you. Known variance, okay, known. I would say that this is population variance, population variance. Then level of significance, they give you 4%. Now find in terms of x, sigma and n, the set of values of k for which mu equals to k is rejected. Now they give you this conclusion. Okay, conclusion given. Okay? Like I said, just follow the steps. Okay? So, step 4 is to write the test statistic. I will write this. Test statistic, when H naught is true, first we know that your test statistic must be you always write x bar minus this k, k, correct? Divide by what? Now, you know this variance, this is a population variance, so it must be sigma over root n. Correct? The therefore sign, is it printed for you? Don't need, I don't need the therefore sign. Okay? When H naught is true, then this is your test statistic, you are going to do a Z test. You should be able to write this down. Z test, right? Because it's a known population variance. Clear cut, you do a Z test. Follow what I'm saying? Can? Just write this. There's nothing, just write this. Okay? Next, you do computation. This is the part that you have to understand a little bit more. In normal situation, what do? We say, we calculate p-value. But there's no p-value to calculate. You only know the conclusion. Correct? You know the conclusion. The conclusion is that you reject H naught. So, look here. This is the Z curve. This is the standard normal curve. For you to reject H naught, it must fall in your rejection region. And because it's a two-tailed test, it must fall inside the rejection region either way. Follow what I'm saying?
Follow. Okay. Ignore this complicated diagram for now, okay? Wait. What I'm trying to tell you is this. Now, there must be some rejection region here. This is your Z, correct? For you to reject H naught, your Z must be here or here. But before that, are we able to calculate these two critical value? The critical value of Z. We should be able to. How? From your level of significance. Your level of significance is 4%. Correct? Your level of significance here is 4%. Now, we all should know by now, if you want your level of significance to be 4%, this rejection region must take on 2% here, 2% here. Follow what I'm saying? So, your critical Z value, you just have to inverse norm 0.0201. This is your mean, this is your variance. Correct? This is your Z. Then you realize that you will get a value. Anyway, don't need to copy, it's all in your notes. Negative 2.0537. By symmetry, this must be 2.0537. Follow what I'm saying? Yes? By symmetry, the other side must be 2.0537. So, therefore, I'm going to write here now. The standardized value of Z, X bar, must fall in the rejection region. Okay? What is the rejection region? Again, Z. The rejection region is this. Z must be smaller or equals to negative 2.0537, or Z must be greater or equals to negative 2.0537. But this is the standardized value of X bar. How do you calculate Z? That's where your test statistic come in, right? Right? That's where your test statistic comes in. Look here, that's why I always force all of us to write this. The small Z value can be calculated using the small X value here. So, very brainless, you just substitute your X bar in. Here, your small Z value is related to your small X bar value like that. Sorry, this one no minus. Anybody blindly copy? Check whether you are awake. Just testing really. Okay? So, this is your standardized value of X bar, standardized value of X bar. All you need to do is to manipulate. Okay? Can? So, due to time constraint, I will just give you ... Okay? Set of values is this. Okay? Just ... The question asks for set of values, you just reply. Just answer set of values. Okay? It's only this last part that's a bit different. The rest is quite standard. Example 10. In a rice packing factory, machines are known to deliver each set an amount that is normally distributed. Population is X is normal. Alright? And standard deviation 1.95. This is a population standard deviation. Again, we know population standard deviation. You take n equals to 50, correct? You want to check whether it is in excess of 25 kilogram. This is a very standard problem. You do a one-tail test. Why one-tail test? Because here, in excess, that means you do one-tail test. Using a 5% level of significance level test, 5%. Again, you know about set. Don't forget set of values, you must give the curly bracket thing, okay? Okay, part 1 is rather standard. I'm going to go through very quickly. Okay? Step 1, define random variable. Step 2, H0 and H1. Alright? One tail test greater than. Step 3, level of significance. Step 4. Actually, if I want to be quick, wait, okay. This one, I want to do something, can I delete this one? Useless one, not useless, like that one. I just need, when H0 is true, just write this. Just write this. Okay, I don't need all this. Cancel. Write this. I only need the test statistic here. Because when we write test statistic, I'm only interested whether you do a t-test or z-test and just standardize it. Follow what I'm saying? Okay? Step 5, computation. Alright, now, the question did not ask you to conclude because the question did not even give you your sample mean. There's no way of computing. Follow? Right or not? Let's look at the problem. See. This is your population. This is your sample. The question asks us, what is the set of values for the sample mean which would lead to the conclusion that the machine has not over-delivered? Oh, what a mouthful. Let's look very carefully. When you set up your test, if you reject H0, then the machine has over-delivered. Let's focus on the word over-delivered. I say one more time, if you reject H0, you are concluding that the machine has over-delivered. But now you want the conclusion that the machine has not over-delivered, which means you do not reject H0. That means you don't want your value, your observed value, to fall in the rejection region. It must fall in the acceptance region. Follow? It must fall in the acceptance region. You sleep so soundly, very obvious, Oh. Yeah. Okay. So, to conclude, so now we all know by now how to find the rejection region, right? Just inverse norm, right? This value, you know how to find this value, right? This value is just inverse norm. Inverse norm what? 0.95. Because you want this to be 0, level of significance for one tail test. This way is 0.05, you inverse norm 0.95, you get 1.6449, this one. So, to conclude that the machine has not over-delivered, you want H0 not to be rejected. Correct? You do not want H0 to be rejected. Because you don't want to conclude that it's over-delivered. Therefore, you want it to be here. Which means if you want it to be here, you want it to fall outside the rejection region. Therefore, your Z must not fall inside here. Therefore, must be here. Must be here. Correct? It must be smaller than 1.6449. Because if it's inside here, you will reject. When it's here, you will not reject. Then you just standardize your X bar, just substitute in. Eventually, you get an answer here. Only a one-tail answer. That means as long as your sample mean, look very carefully, as long as your sample mean is less than 25.454, this is, you want to conclude whether it's 25 or not, right? Correct? 25 or larger than 25. So as long as your sample mean is 25.454. As long as your sample mean, you observe the mean to be around here, around here, or here, as long as you observe your sample mean here, then you will not reject H0, then you will not conclude that it has over-delivered. Or rather, you conclude that it has not over-delivered. But why is there a 0 here? Yes, x is weight. X is weight. So to be complete, we put this one. Okay? Because x is weight. X cannot be negative. Okay? Part 2. State with the reason whether central limit theorem has been used to obtain this set of values. Have we used central limit theorem? Did we use central limit theorem? Throughout our calculations, have we used central limit theorem? Yes or no? Okay, I want you all to make a choice now. Think, if yes, put a right hand, no, put a left hand. Cannot put up both hands. Both hands means surrender. Ready? Make your own judgment, okay? Yes, put a right hand, no, put a left hand. Everybody must put a hand. Don't put out hand. Buy the cup of coffee. Then for the next 1 month, I don't need to pay for my coffee. Ready? 1, right hand, yes. Left hand, no. 1, 2, 3, go! Coffee. 4, 5 coffee. Hey, remember, 1 coffee. How many coffee? 6 coffee. 6 coffee. Very good. Put out your hand. Have 6 coffee. And counting. Okay, you remember it? Coffee, Coffee C, okay? Okay. No. Why? You're right. Because it is already normally distributed. Population mean known. Population standard deviation known. So, did not use. Copy. Not copy. Copy. Part 3 is the most difficult one. Very hard to explain. But never mind, I will try. Okay, done? Can copy? So few words. Okay, play once, twice. Sorry, I have to entertain myself. Not entertain you, I entertain myself. Okay. Part 3. Using the set of values for the sample mean found in 1, read the problem together, okay? You need to find the probability of not rejecting the null hypothesis, when in fact the machine is delivering a mean of 26.4. You see, also scared. I don't know why they're not asking, right? I tell you something, when I was, very interesting, I was going through this halfway with the other lecture group on Tuesday. Hey, went through, very good, right? I spent everything until part 2. Then part 3, I start don't know how to explain. I didn't know how to explain. Then luckily, just at that point, the bell rang. Then I said, I'll explain next section. So actually quite difficult to explain, or even to understand. But I told them the truth. I told them actually I didn't know. I mental block. Really, I'm very honest. I must tell you all the truth. I really mental block. Then at that point I couldn't. Okay. So anyway, okay. What? Okay, I hope I don't mental block now. No bell to save me. Yeah. No mental block. I know exactly what I'm doing. I just want to think of a best way to tell you. See, you did a test in part 1. Thank you. You did a test in part 1. If your X bar, if sample mean fall between 20 and 25.4, you will conclude that actually you conclude you will not reject H naught. Correct? Basically that was what we found in part 1.
Correct? That was part 1 I found. To summarize our answer part 1. If your sample mean found was between 0 and 25.5, you do not repeat it, you won't reject it. But in part 3, you're asking the same thing. You want to find now this time you want to find the probability of not rejecting H naught. Which means you want to find the probability of this happening. For example, one more time, in part 1 you found that if this is like that, you do not reject H naught. But now in part 3, you want to find the probability of not rejecting H naught, which means you want to find the probability that the sample mean is between 0 and 25. You are given one additional information. Now, given that the population mean is 26.4, they're starting to test now. It is a certain thing that the population mean is 26.4. So essentially, don't copy it. Essentially, what do you want to find? You actually want to find probability X bar falling between 20 and this, given that mu is just 26.4. To summarize, this is what we want. Follow? Good. Then we do it. If mu is 26.4, that means the population is 26.4, what we are saying is X follows this normal distribution with mean 26.4. Correct? If X follows this distribution, X bar should have the same mean 26.4, but will have a different variance, which is 1.95 squared over n, which is 50. Correct? So now, in order to conclude that you don't reject H naught, it's equivalent to finding this. I'm going to use the 5SF figure, okay, for accuracy. Okay, this is the 5SF figure. Then you get a probability which is 0.000301. Okay, if you can understand this, very good. Okay, almost difficult part, which also means I explain quite well. Okay.